In the previous part, we introduced the aggregate loss model, which is about a summation of IID variables, but the number of terms in the summation is random. So in this part, we consider a special case where the number of terms is not random but deterministic. So this is about convolution. Okay, so we consider the easiest case. Suppose we have two independent variables x and y, and suppose we know their distributions. So we want to find out the distribution of the sum. So if x follows fx and y follows fy, then what is the density of the sum S? Okay, so in order to solve this, we use the technique of double exploitation. Okay, so we first write the CDF of S in terms of the probability, and then probability in terms of the expectation of the indicator function. Okay, and then we write this expectation as a double expectation. We condition on x. Okay, so now to evaluate the inner conditional expectation, we consider conditioning on the event x equals x. Okay, so now it becomes the probability the sum S less than t given x is x. Okay, in this case, y less than t is the same as, S less than t is the same as y less than t minus x. Okay, because S is capital X plus capital Y. So if capital X is equal to x, then y must be less than t minus x. But then x and y are independent. Okay, so now we can throw away this condition. It becomes the CDF of y evaluated at t minus x. Therefore, the inner conditional expectation here equals this fyt minus x, but with this small x replaced by the random variable x. Therefore, the CDF of S is just the expectation of this inner conditional expectation, fy of t minus capital X. So this is a function of capital X, a random variable. So to evaluate this integration, we use the the density of x. So it is just the integral of the density of x times this function, okay, and then dx. So you can see we can find out the CDF of S from the density of x and the CDF of y. But x and y are symmetric, so we can also change x to y and y to x. So we can also write it as the CDF of S being the integral of the density of y times the CDF of x. So if you look at this formula, it's actually very natural and very easy to interpret. Now we are finding the probability that S equals t. So what we do here is to condition on x. So suppose x is x. Then in order for the sum to be less than t, the other variable y must be less than t minus x. And then we sum over all possible values of x, and then we get the probability. So in a sense, this is just the total probability formula. Okay, so now we know how to find the CDF of S. Now if we differentiate both sides of this equation with respect to t, we will be able to obtain the density of S. So now let's do it. So if we differentiate both sides with respect to t, then the left-hand side becomes the density of S. And then on the right-hand side, so we need to differentiate this guy with respect to t. It becomes this density of y, and then that's t minus x. Or using the second formula, we differentiate this term with respect to t, and then we get the density of x. Therefore, the density of S can be obtained by either one of these two equations. Okay, again, it is very natural, very easy to interpret. We want to find somehow the chance that S is t. So if x is x, then y must equal to t minus x. And then we sum over all possible values of x, and then we get the chance that S equals t. So now we look at one example. So this is about exponential. Suppose we have two IID variables following exponential with mean theta. So we want to find out the CDF of the sum, x1 plus x2. Now if they are IID, so we use this symbol. So fx and then star2. Okay, so star2 means that we are adding up two IID copies of the variable. So using our formula, so this CDF of the sum can be obtained from integrating the density of one variable times the CDF of another variable evaluated at x minus y, and then we integrate this over y. Now here I haven't written down the upper and lower limit, so we need to look at these two factors. So if we look at the first factor, you can see that whenever y is larger than x, this is 0. The second term will be 0 if the argument y is negative. Therefore, the product will be 0 whenever y is larger than x or less than 0. Therefore, this integral is only non-zero when y is between 0 and x. Okay, so now we replace the CDF of x and also the density of x by the respective formula. And then the rest is just algebra, so we can integrate this easily and then we can obtain this. So this is the CDF, the density, the CDF of the sum x1 plus x2. Now let's move further. Suppose we have this time an IID sequence of the same exponential distribution, and I want to find the density, okay, the PDF of the sum x1 up to xn. Okay, so the symbol is f star n. So we are looking at the density of a sum of n IID copies of x. So we want to show that the density is given by this big expression. Okay, so how to do this? Because we want to show this is true for all n, therefore it's natural to consider using induction. So we first check whether the formula is true when n equals 1. Okay, so if we put n equals 1 in the formula, you will see that the formula will give us 1 over theta exponential negative x over theta, which is of course the PDF of 1 x. Therefore, the formula is true for n equals 1. And now to apply induction, suppose the formula is also true for n equals k, and then we look at f star k plus 1. So this is the density of a sum of k plus 1 IID copies of x. So using our formula, okay, so if you want the sum of these k plus 1 copies equals x, okay, let's say one of them is t, then the rest, okay, the sum of the rest must equal x minus t. And then we integrate over t, and this will give us the required probability. As before, okay, we need to look at each factor and determine when it will be 0. So the first factor will be 0 when t is greater than x. The second factor will be 0 when t is less than 0. Therefore, I can write down the lower limit as 0 and the upper limit as x. And then this factor by our induction hypothesis, because we have assumed that the formula is true for k equals n. So I have a formula for this. So I just plug in the given expression. This is just the density of one exponential theta variable, okay, and I know that the density is like this, okay, and then, well, this is pretty easy to integrate. You need to put things outside, so those irrelevant factors, those factors not depending on t, we put them outside, and then inside, the only factor left is x minus t to the power k minus 1. You can integrate this easily, simplify it, you will get this, which is exactly the given formula for n equals k plus 1. Therefore, the formula is also true when n equals k plus 1, and therefore by the induction, by the principle of mathematical induction, the formula is true for any n. So in the next part, we will look at some examples involving discrete distributions.